Yes.
All right, great. Okay, so to start with, I'm going to remind you of some horror stories. Back in the 80s, there was this medical machine called the Therac 25, and it could do both radiation and X-rays. And between 1985 and 87, there were 6 times where someone received radiation when they were supposed to receive an X-ray, and they got a really bad overdose. In 1996, there was a famous example of a Ariane 5 rocket, which exploded shortly after liftoff. And the value of the rocket and cargo were estimated at least 500 million. And then back in 2003, when I was living in New York City, there was the largest blackout in the history of the US, where the entire northeast of the United States had a power outage, and the estimated cost in New York City alone was over $1 billion. So what do these horror stories have in common? Well, they're all caused by software bugs. So it turns out there was a bug in the controlling software for this Therac 25 machine, so that if you hit a certain sequence of keys, there was a plate that was supposed to come down to turn the radiation machine into an X-ray machine, and the plate did not come down because of a bug in the software. The Ariane 5 explosion, embarrassingly, was the result of an unsafe conversion from floating point to integer in the software system. And the blackout was actually at least partly due to the fact that an alarm system that was supposed to alert First Energy in Akron, Ohio, had a bug in it. And so what was happening is it was filling up the logs with error messages so fast that it rebooted the machine, and none of the error messages ever made it to the monitors, so nobody ever saw those error messages. Okay, so well, I could tell you, and I'm sure you could tell me, lots of stories about software bugs and how bad they can be. So now what about AI systems? Well, AI systems in some ways are even worse. So we've learned a lot about how to do good software engineering. And often when there's a bad bug, it's because somebody didn't follow best practices, not because the best practices failed. But now with AI components, we have even more challenges. Consider, for example, AI components built with deep neural networks. So many of the traditional software engineering techniques like code reviews, code coverage, programming with assertions, modular programming, they're just not applicable to these kinds of systems. In fact, neural networks are such complicated artifacts that humans really don't understand what's happening. So we can sort of observe what's happening at the interfaces, but we don't have a good intuition for the actual function that's being computed. So how do we ensure that these systems are safe and correct, especially if they're going to be used in safety or mission critical applications? And that's sort of the big question. I don't have all the answers, but it's the big question I want to ask and talk about today. So to start with, I'd like to introduce the Stanford Center for AI Safety. And the mission statement is to develop rigorous techniques for building safe and trustworthy AI systems and establish confidence in their behavior and robustness, facilitating their successful adoption into society. So that's our mission statement. It's very lofty, but we think that it's an important goal, and that there are a lot of things we can do along this pathway. And the faculty directors of the center are myself, Michael Kokendorfer, and Dorsa Sadiq. And with their permission, I'm going to play a couple of videos about some of the work going on in their labs, and then I will tell you about some of the work that I'm doing. So that's the basic overview of the presentation today. And just to kind of give you a flavor for what are the things that the center is interested in. So we're interested in using formal methods for AI safety, including specification, verification, and verifying whether something is robust against adversarial attacks. We're interested in learning and control for AI safety. So how do you do safe learning, safe exploration, safe planning, things like that. And then also things like transparency, so fairness, explainability, and diagnosis and repair. Okay, so I'm going to start with some of Michael's work. And of course, Michael does a lot of work. He's a professor of aeronautics and astronautics, and also by courtesy computer science. He has expertise in collision avoidance for aircraft, as well as lots of different interesting AI techniques. And he's gonna, in this video, he'll give a brief overview of sort of the high level things that their lab is working on. And then one of his students will talk about a specific project about AI safety for autonomous vehicles.
Hello, my name is Michael Kokendorfer. I'm one of the co-directors of the Stanford Center for AI Safety, and we'll be providing an overview of some of the projects we have been working on over the past few months. In our lab, we work on the mathematical models and algorithms for decision-making under uncertainty for safety-critical systems. We're interested in modeling, planning, and verification. Modeling involves going from data, such as aviation radar data, or LiDAR data from an autonomous car, to some kind of probabilistic model. In some cases, there may be inadequate data, and so we sometimes need to incorporate human expert judgment into the construction of our models. These models may range from Bayesian networks to generative adversarial neural networks. Planning involves taking these models to derive a plan. In problems where there is uncertainty, we generally want the plans to be reactive to how the environment evolves and robust to perceptual uncertainty. Validation involves going from this plan to some degree of trust that the system will behave as we intended when deployed in the real world. We'll be highlighting some research that we have done these past few months in these three areas of modeling, planning, and validation. My PhD student, Anthony Corso, will describe some of the research we have been working on involving automotive safety validation with adaptive stress testing.
So one of the major problems in autonomous driving is how do we validate the safety of these systems before deploying them on the road? Errors in perception, planning, and control can cause complex failures that may have been difficult to anticipate. So while traditional testing techniques are surely needed, we may also need automated and adversarial testing techniques. But adversarial testing techniques come with their own set of challenges. Number one is that they might find unrealistic scenarios. So consider this situation where a vehicle is driving down the road and encounters a pedestrian that's trying to cross. Our technique, adaptive stress testing, found a failure mode where the pedestrian decides to run headlong into the vehicle, which is coming to a safe stop. So I think we can all agree that this failure mode is probably not first on our list of things that we want to actually solve. The other problem that automated testing suffers from is scalability. So there are a vast number of possible driving scenarios that our autonomous vehicle can encounter. And even in a single class of scenarios, so for example, in this intersection scenario where the ego vehicle in blue is trying to take a left turn, there may be as many as 10 to the 13 different configurations of 5 vehicles on the road. So it's going to be totally intractable to enumerate all of the possible configurations of a given scenario. So to overcome these challenges, we first have to frame our problem as a Markov decision process so that we can solve it with reinforcement learning. So this is really the heart of our technique, adaptive stress testing. We have a simulator that contains within it an environment that the vehicle is going to be driving in, and the environment can contain things like other agents on the road, as well as sensor noise and other perturbations that could affect the behavior of the driving agent. And then we have the system under test, which is the ego vehicle that we're trying to stress test. Outside of the simulator, we have a reinforcement learning algorithm that's able to perturb the environment through an action and observe a reward. Now, we designed this reward function so that the rewards are high when we get situations where the system under test does something unexpected or has some sort of failure. So the reinforcement learning algorithm is trying to find situations that are challenging for the driving agent. So to address the first problem of finding unrealistic scenarios, we can take our reward definition and alter it so that it incorporates something known as responsibility sensitive safety, or RSS. So RSS is basically a set of common sense driving principles, such as don't rear end someone and right of way is given, not taken. And it turns those into formal mathematical statements about which actions are acceptable at a given time step. So what we can do is look at the actions of our system under test and see whether or not they are appropriate according to the RSS rules. If they are not appropriate, then we can be rest assured that something is wrong with the policy that we're running on the system under test, and we'll have found a failure that is actually relevant rather than one that is somewhat contrived, like the example I previously showed. Then the last challenge that we have is scalability. So to address scalability, we've taken the approach of decomposing the scene into a bunch of subproblems that are all in of themselves tractable. So what we can do is pair off each other agent on the road with the ego vehicle and then find failures for that smaller problem. Then we can go back and combine all of these subproblems together and fuse their results in a way that allows us to find failures of the more complex scenario. Okay, so to look at some results, if we apply our RSS metric into the reward function, we now find a very different failure mode in that same scenario that I showed previously. In this case, the adaptive stress testing algorithm finds a mode in which sensor noise tricks the ego vehicle into thinking that the pedestrian is still on the crosswalk or on the sidewalk, but when in fact the pedestrian has entered into the road, causing a collision. So this failure is much more relevant and is something that we'd like to work out before we deploy that vehicle on the road. The next shows results from our scene decomposition approach, where we are able to find failures in this complex 5-car environment using failures found in the 2-vehicle interaction for each of these 4 other agents on the road. And we can actually use this technique to generate a lot of failures and therefore get statistics about how likely it is that our ego vehicle fails. And so this plot shows our estimate of the probability of failure of that ego vehicle versus the number of samples required. And we see that our approach in purple is able to get an accurate estimate of the probability of failure in just about 10 samples, while the other techniques require almost 1,000 samples or don't get a good estimate at all. So with that, I'm going to conclude with 3 points. The first is that we can perform automated testing using adaptive stress testing on automated vehicles to find complex failure modes. But we need to incorporate some common sense driving principles in order to guide the search towards important failures. And lastly, we can use scene decomposition techniques to solve the safety validation problem in complex driving scenarios.
To conclude this presentation, I would like to point you to some additional resources. So the first is a survey of algorithms for black box safety validation. This survey was led by Anthony Corso, and it encompasses many of the emerging research directions. We have also been involved in the building of a number of driver models using generative adversarial imitation learning, and a synthesis of the work that we have done along these lines. We have also done a survey on driver models in general, and we have posted this survey on arXiv. It took about 2 years to write. I'm also really excited about a preprint becoming available of a new book titled Algorithms for Decision Making, where we talk about POMDPs and Markov decision processes, Bayesian networks, as well as validation. If you're interested in receiving a PDF copy when it becomes available, you can register your interest on algorithmsbook.com.
Okay, so that is Michael and his lab. So I'd like to thank him for preparing this video.
Hello, my name.
All right, so now we're going to go and hear a little bit from Dorsa, the other co-director of the Center for AI Safety. And Dorsa's work, she does a lot of different work, but the work she'll be talking about is primarily in interactions between autonomous systems and humans, or more specifically between robots and humans. And there's an important safety component, obviously, whenever you have an autonomous system interacting with a human. And Dorsa's work does look at some of those safety concerns, but I think a lot of the work she'll talk about is even more fundamental. How do you even think about these kinds of interactions between humans and robots? How do you model them? How do you get the robots to learn from the humans to interact with the robots? So she'll give you a brief overview of some of the things in that direction.
All right. So hi, everyone. So today what I'd like to talk about is two main categories of work that we have been working on this past year. One is around learning human preferences, where the human is this teacher with many sources of data, and the robot is just trying to learn from the human. And the second perspective is more of an interaction perspective, where the human and robot are symmetric agents in a dyadic setting. They're trying to do a collaboration together. So let's just get into it. When we think about learning human preferences, you might be thinking about learning a reward function or learning a policy. And we usually do that based on having access to expert demonstrations. Imitation learning from expert demonstrations has been around for more than 2 decades now. But we have been looking at a few set of other directions where we don't assume that we only have access to expert data, but we assume that we can have access to a lot of different variety of data and tap into these different sources. So first, we've been looking at this idea of learning from suboptimal demonstrations, where we have access to both expert data as well as data from different dynamics, the robot with different dynamics, or suboptimal data. And based on these demonstrations, we have a notion of optimality and feasibility. And based on that, we score the trajectories and we do imitation learning. We've also been looking at other sources of data. For example, what can we learn from language instruction? So Sid has been working on this problem where we can interactively teach a robot how to do a task. For example, when a person comes in and says, wash the mug, can the robot interactively learn from that? And how can we do that based on decompositions? So if a person comes and decomposes that task, how do we use these decompositions together in order to figure out what is washing the mug and what is not washing the mug? And then based on that, how do we update our model in an online fashion? So if the robot comes and says, wash the mug again, we would be able to do that. Moving forward, there are also other types of data, for example, pairwise comparisons, rankings, or ordinal data that we can rely on. And Erdem has been looking at this idea of active preference-based learning based on these types of queries, pairwise queries, where we show two different trajectories, A and B, and then we ask a user what your preferences are. And based on that, we are trying to learn an underlying reward function. The thing is, if this reward function is linear in a set of features, it's not able to capture a variety of tasks. In this case, it's not really going to be able to capture these different targets that the robot is trying to push the golf ball into. So what we've been looking at is using Gaussian processes here and doing active preference-based learning over Gaussian processes. The detail of this is in this RSS paper, but I just want to show you how this works in practice. So if you use a linear reward, the robot only targets the sites. But if you use a Gaussian process reward, we are able to capture any of these targets that we have down the line here. Finally, another type of data that we can have access to is physical correction. So a robot is not really an AI agent, right? It has an embodiment. So because of that, we can actually move it around. And what Munshi has been looking at is when we have multiple robots coordinating with each other, trying to do a task incorrectly. For example, let's say they're trying to help us unpack these groceries, but not based on humans' preferences. How can the human provide feedback and a sequence of physical feedbacks? And the fact that how can we learn from these sequence of physical feedbacks and interdependencies between them in order to better learn a reward function or human preferences? Moving forward, another idea that we have been thinking about under interaction is how to capture risk-aware human models, specifically how humans act in near accident scenarios or when there is some notion of risk. The idea is, so far, I've been talking about learning reward functions, and I've been assuming that humans follow some sort of optimal action or they're rational. Maybe like in best case scenario, they're noisily rational. But the thing is, this still doesn't capture the fact that sometimes the most likely action of the human is something that is suboptimal. So what we've been looking at is developing risk-aware models based on ideas from prospect theory that captures this risk awareness and this type of suboptimalities of humans. So Manet has been experimenting with this on various types of tasks like autonomous driving as well as block stacking, where a robot correctly detects human suboptimalities and coordinates well here. Another idea we've been looking at under interaction is this idea of learned representations and the fact that they can help us for better coordination. Dylan has been working on this idea of learning latent actions for the setting of assistive teleoperation, where we have a set of demonstrations from an expert or a caregiver. And based on that, we are learning this latent representation, latent low-dimensional action in order to be able to do various sorts of assistive teleoperation tasks. Dylan has also looked at integrating this with shared autonomy in order to do more precise tasks like picking up food or looking at feeding at the moment. This idea of representation is also pretty powerful when it comes to coordination with other agents. We've been looking at that for this various settings like coordination and influencing between humans and robots or robots and robots for various types of competition and coordination tasks. And finally, the last topic that I just want to briefly mention is something that I'm very excited about, this idea of repeated interactions. I feel like we don't think about it that often. And Andy is thinking about this idea of repeated interactions where we have games where there are elements that are specific to the rule, but there are also elements that are specific to partner, and we are trying to learn what are partner-specific conventions that we can learn. Just like driving on the right side of the road is a convention, what sort of conventions can be learned here? With that, I'd like to thank the group, and I'm going to thank you guys.
Okay, great. So that's just a taste of some of the things happening in the center from my colleagues. And again, I'd like to thank Dorsa for preparing this video. You know, as you can see, there's lots of interesting things going on, lots of things related to, you know, safe interaction and operation of autonomous systems. So with the rest of the time, I'm going to talk about some work that we've been doing in my lab on using formal methods in AI safety. So first of all, just to make sure we're on the same page, let me tell you what do I mean when I say formal verification. And I think of it as 3 steps. So the first step is to have some kind of mathematical model of the system that you want to verify. And that sounds hard, but actually if your system is pure hardware or software, or a combination of those two, it's actually very easy because a software artifact or a hardware artifact has a formal semantics. And so you already have a formal mathematical object. Now, if you're dealing with some kind of physical object like a robot or an airplane, this part becomes more difficult. But the good news is that, you know, a neural network is a mathematical object. So this part is easy for that. The next step, step 2, is to specify formally what the properties of the system should be. Now, this may be simple or it may be very difficult, right? And this is one of the challenges I'll come back to. And then finally, step 3 is to prove that the model has the desired property. And this is a mathematical proof. So if you can do it, this is much better than testing because it covers all possible cases. Of course, it's only as good as your properties, right? So if you didn't think of some property and you didn't prove it, there could be some problem. And one piece of good news is that there have been a lot of advances in automated reasoning, which makes this third step much more scalable and tractable than it has been in the past. And now this is, of course, something that I work on, and so it's exciting that there's been progress in that area. All right, so to sort of understand how to put this together in the setting of, say, verifying a neural network, I want to look at a simple example. So here's an example of a very simple neural network with 1 input, 1 output, and 1 hidden layer with 2 nodes. So step 1 is we need to, that should say we should create a model of this system, right? So the model is basically going to be representing each node of the network with a variable. For the internal hidden nodes, because they have these activation functions, and here we're going to consider rectified linear unit, or ReLU, we have to split those into 2 variables, one for the input to the activation function and one for the output from the activation function. And then we can actually just write a set of equations that describe how these variables are related to each other. So for example, we would say that the x2w, which is the weighted sum for x2, is just equal to the input x1. And we write the equation x2w minus x1 equals 0. Similarly for x3w, and then we write this equation for x4 that just says it's the weighted sum of the 2 outputs. We can also set some bounds. So we know, for example, that the outputs of the rectified linear unit have to be non-negative. So we can set bounds on those variables that they are greater or equal to 0. And then finally, we have some special constraints for the rectified linear units. Essentially, we represent those with this if then else construct, saying that the output If the input is greater than 0, the output is equal to the input. If the input is less than or equal to 0, then the output is 0. So this ITE if then else just takes 3 arguments, which are the if part, the then part, and the else part. Okay, so this is now a model of the network that completely captures, everything about that simple network. And you can build models like this even for very large, complicated networks. All right, so step 2 would be then to specify what are the properties that this system should have. Now here I'm just going to assume some simple property, some simple input-output property, like if the input is within the range 0 to 1, then the output should not be within the range from 1/2 to 1. All right, we're going to try to check to see whether that property holds. And the way we do that is we actually negate the property and try to find a counterexample. So what we're going to do is we're going to set the bounds that x1 should be within 0, 1, but then we're going to try to force x4 to be within that forbidden range from 1/2 to 1 and see if that's possible. If it is possible, then the property does not hold. If it's not possible, then the property holds. Okay. Now, this particular example belies a larger challenge with this second step of specification. So in general, it may be very difficult. And why is that? First of all, you may have an easy way to specify something about the system, like the car doesn't crash or hit a pedestrian. But how does that map to a property on a subcomponent of the system, which is this learning component? So that can be quite challenging. The other thing that could be challenging is maybe the property is something that you can't specify formally at all. For example, if you have an object recognition network, how do you prove that it always correctly detects a cat when we don't even know what are the right parameters that would describe a cat versus not a cat? And the thing you care about most may not have any formal specification at all. So this is a big challenge for applying formal methods to neural networks, but there is a good place to start. And a good first step is this property of local robustness. So local robustness just means that you have some known data point where you know what the input and output are supposed to be. And what you would like, and this is a property that most networks, we would like to have this property, is that in some small neighborhood of the input point, the network should behave similarly, right? So you don't want to have a bunch of input points that all say it's a cat, and then have some point between those two input points that gets mislabeled as something else, right? So what's great about this property is you can specify it formally and you can check it, and you can do this for pretty much any network. So formally what it says is if the difference between a known input x0 and the current input x is less than or equal to some delta, then the output classification should stay the same. Okay, and then step 3 is to prove that the system satisfies the property. Okay, now how do you do this? Well, you need some kind of proof engine. Obviously, you can't do this by hand, right? This is going to be way too complicated. So we need to bring automated reasoning to the rescue here. And we need an automated reasoning tool that can reason about linear arithmetic, because we use linear arithmetic to model the network itself. We need to reason about some limited nonlinearity, like these activation functions, like the rectified linear unit. And so what can do that? Well, off-the-shelf solutions like mixed integer linear programming or SMT solvers can, in principle, reason about these, reason in these two, about these two things. But the problem is that they really can't handle it efficiently. So when we first tried to look at this problem, we tried these things and it just didn't scale up at all. So what I'm going to show you is an example of an algorithm that we devised called the Reluplex algorithm, which takes a known linear programming algorithm simplex, and it modifies it to be smart about these activation functions. And I'll show you how this works. So what we've done here is I've got the equations from this simple example. And then we have this table here that shows a proposed assignment to each variable. And each variable also has some bounds, right? And so we're going to try to find a way to satisfy the equations and satisfy the bounds at the same time. Now, these blue arrows show the two variables that are related to the input and output of the rectified linear unit. And we're going to, in addition, try to keep those in sync. And that's the twist. So I'll show you how this works. So to start with, we find a variable that's out of bounds. Okay. So note that this x4 variable, the current proposed assignment is 0, when it should be between 1/2 and 1. So what we can do is we can just do this update operation to the assignment that changes x4. Now, of course, we have to look at the equations and also update anything that depends on x4. And in this case, that would be x7. So x7 also gets increased by 0.5 because of that equation. Okay, so good so far, except now x7 is out of bounds. So let's see if we can fix that. Now to fix that, because x7 is on the left-hand side of an equation, we first have to pivot it so that it's on the right-hand side. So if we pivot it over here, now we can update it. So we can reduce it down by 0.5, which we do. And that's going to affect this x2a variable. Now, once we change the x2a variable, the ReLU is no longer in sync. So we have to update this partner variable of the x2a. Remember, the x2w is the input, the x2a is the output. So if the output is positive, then the input had also better be positive and equal. Okay, so we update that. But of course, now we have to look to see how does that affect other variables? And it affects x5. So x5 gets incremented to 0.5. And now that's out of bounds. So we're going to pivot and update x5, which we do. That's going to affect both x1 and x6. So we update both of those, x1, x6. x6 is out of bounds. We pivot that with x3w and fix that one. Now notice here that when we change x3w to negative 0.5, the output is 0, and that's okay, because for a rectified linear unit, if the input is negative and the output is 0, that still satisfies the constraint. So in fact, we found a solution, okay? And so there is, it is possible for the input to be within 0, 1, and for the output to be within 1/2 to 1, which means that the property that said that that was not possible does not hold, okay? So we found a counterexample. All right, so that gives you a little taste of some of the work that we did to come up with an algorithm for verifying networks. And this is actually an exciting new research area. So there's quite a few people working on this, building specialized solvers or techniques, pre-processing techniques that target backend solvers for somehow being able to verify neural networks, prove things about them, find counterexamples, find adversarial inputs, and so on. And some of the techniques are based on reachability, some are based on search, some on optimization. There's work being done on parallelizing these, and so on. So there's one nice overview at this archive paper that you can take a look at. And I also am happy to talk to people about this later. All right, now I want to tell you one case study of what this is good for, and this is actually the case study that motivated this work in the first place. And this is joint work with Professor Kokendorfer. So basically, the idea is he wanted to come up with an airborne collision avoidance system for drones, and working with the FAA on that. And the idea is you have some drone flying in the air. It has some sensor data about potential intruders in the airspace, and you want to give that drone an advisory of what should it do. It could be that there's nothing nearby, so it can just keep flying on its mission. It's the clear of conflict advisory. or maybe it needs to turn, either a strong left, left, or a strong right, or right. Okay, so those are the possible advisories. And for various reasons, Professor Kokendorfer was considering using an implementation with 45 neural networks. They aren't that big. They're about 300 rectified linear units in each network. But the nice thing about the network is it actually had better performance and was much smaller and more compact, so it took up less memory, and both of those were important for this system on drones. Okay, but obviously, you know, it's a little bit scary to the thought of implementing this with a neural network where, again, we don't have this sort of intuition or transparency. So how could we verify them? So the idea was to try to prove that certain properties would hold for all possible inputs. Like if the intruder is distant, then the advisory is always clear of conflict. Or if the intruder is nearby but on the left, the advisory is always strong right. And this kind of proof we considered to be a crucial part of increasing the level of confidence in this implementation. All right, so I'm going to show you an example of what we did with that. But first I want to mention we've implemented all of this in an open source research platform called Marabou. And this includes its own custom linear programming engine, support for various piecewise linear functions like ReLU and Max. It accepts input formats from various different tools like TensorFlow. And it has some parallelization and so on. So this is an open source project. You can find it on GitHub. And then let me show you one thing that we did with this. So what we could do is for this collision avoidance system, we did the following experiment. We said, let's start with an intruder who's far away, maybe 90 seconds away from the main drone. And we're basically going to take the entire space of possibilities where that intruder could be and turn it into a grid. Now we're going to assume that that intruder is in one of these grid points far away. Now what we do is we use Marabou for each of the possible boxes that the intruder could be in. We ask what are the possible next boxes it could be in one time step later. And I think the time step here is 1 second. So if our aircraft follows the advisory and the intruder basically stays on its trajectory, then what are the possible next steps that could happen? And then you just keep doing that every second until you get to the point where there could be a collision and try to see what are the possible scenarios, okay? And we visualize this. So the red dot here is the near midair collision dot around the drone, okay? And what we're showing you is basically starting at 90 seconds away, where could the intruder be if I follow the advisory? And yellow means there are lots of ways that the intruder could be in that space. Blue means less ways, and white means there's no possibility that the intruder could be in that space. And what you see is that by the time we get to 0 seconds, there's a nice white area around the red near mid-air collision circle. And so what this actually does is this is actually a proof, a visual proof that there's no way for there to be a collision as long as the intruder stays on their path and the drone follows the advisory. Okay, great. So let's see. I wanted to talk just a little bit about some recent work here where we parallelize this technique and this is a nice technique because it's actually quite general. So the idea is you've got some big question that you want the solver to solve, and it's a hard question. So what we're going to do is we're going to do this divide and conquer algorithm. And the idea is you first use a small timeout and try to solve the entire problem. And that's going to not work. So it's going to fail and say, I couldn't solve the problem. So then what you do is you do some partitioning of the problem. So let's say we partition it into 4 subproblems. Then we increase the timeout a little bit. Okay, so now let's say that 2 of those subproblems we're able to show they're unsatisfiable, they don't have solutions, but the other 2 time out. So for each of those 2, we divide it further, right? So you can keep doing this And basically what this gives you is a way to solve these hard problems by partitioning them into simpler problems. Now, there are several questions about how you would implement this. The first is, how do you do this partitioning? So one way to do the partitioning is what we call input interval splitting. And what that means is you basically look at the inputs to the network and you divide those inputs into half spaces, right? Now, this actually works pretty well, and we have some good heuristics for how to do it, as long as the dimension of the input space is low. So for these ACAS networks, the dimension is, there's about 5 inputs, and this works really well. But for high dimensional inputs, say like a perception network, this doesn't work at all. So we did some new work, and the new idea was, well, rather than partitioning the input, let's actually partition these interior nodes, these rectified linear units, because if we can figure out that one of these is sort of importantly divides the problem into roughly equal parts, then we can just say, well, in one part, let's assume this activation function is active, and in the other, we'll assume that it's inactive, and we solve those 2 subproblems. So one thing we discovered quickly is that it's important to focus on the early layers. And the reason for that is if you fix a ReLU in an early layer of the network, then it has a lot more likelihood of propagating more bounds to later nodes in the network. So you can reduce the size of the problem that way. But how do you choose which network or which ReLUs and which phases? So we came up with this idea of polarity. And basically what polarity does is it's going to look at the current bounds on the variable associated with the activation function. And it's going to see whether the bounds are roughly balanced between the positive and the negative side, or if they're highly imbalanced, right? So if they're balanced, that has a high correlation with giving you a balanced problem if you do a split on this. So we look for polarity close to 0. And we also favor the wider phase because it's more likely to lead to a satisfying assignment. All right, good. Now there's another thing that we can do, which is if we have a bad polarity, then sometimes that indicates a ReLU where one part of the split is trivially unsatisfiable because it has a small range. So we also do this trick where we're going to do a quick check to see if we can solve, assume that one of these ReLUs is either active or inactive with a short timeout, and see if that gives us an unsatisfiable answer. And if it does, then we know that we have to pick the other one. So this is a highly parallelizable preprocessing step that we can do to reduce the overall complexity of the problem. And what this graph shows you is there is a trade-off between how much time you spend doing this preprocessing and how much benefit you get. So, you know, if you do a lot of time doing this preprocessing, the solving time gets short, but the solving time plus preprocessing time might actually be more. So you have to do some trade-off there. Okay, now here's some data showing on a bunch of different networks, including ACAS, some MNIST networks, and some networks that are figuring out how to taxi an airplane down a runway. And what you can see is the ReLU-based splitting is much better than the input splitting on the MNIST and the TaxiNet, which are both perception networks. Now for ACAS, input splitting does okay. Like I said, it works pretty well if the input dimension is low. And then here's showing how well we do with the divide and conquer versus just the standard approach. And as you can see, the divide and conquer scales very well. So there is tremendous benefit from using parallelism on these problems. Now we wanted to try something even more ambitious. And so what we did is we deployed parallelization of Marabou in the cloud. And we used a neat platform being developed by some colleagues at Stanford called GG, which basically allows you to describe parallel computation, and then it uses Amazon Lambda to run up to 1,000 short tasks in the cloud. And what we observed is, again, this was just an initial experiment, but for this we observed that up to about 500 workers, we were able to increase the or decrease the wall clock time. So we got more and more benefit, even up to 500 workers. So again, we think this is very promising. So one of the biggest challenges to formal verification of networks is scalability, but this shows that parallelism could be a good answer to that challenge. All right, so just to say what's next, so we still are interested in trying to scale up right now. These kinds of formal techniques can handle thousands, maybe tens of thousands of nodes, but still there's a big gap between that and the millions of nodes that are used by many deep neural networks. Like I said before, there's a big challenge in specification. What kinds of specifications can we do? And obviously there are some problems that we won't be able to specify, but we think we can do a lot of things beyond local robustness. So we're looking into that. One really sort of key observation is that even for this local robustness property, most networks don't have that property. And so we really need to look more carefully at how do you even train networks to be robust. And there are some people looking at that problem. And finally, we'd like to look at more applications. Okay, so with that, I'll conclude and I'll be happy to take questions.
Thank you for your talk. And